Okay, it's now 3 past the hour. Welcome again to George Mason University's Observatory. To follow us and find out more information to attend future talks available during this pandemic, you can follow us on Twitter at GMU Observatory. You can email us at gmuobservatory@gmail.com for more information, or go to our website at science.gmu.edu/observatory. I'm Dr. Peter Plafchan. I am the director of the observatory, and we normally have these events in person. I hope you're all safe and healthy during quite unprecedented times for us all. And our next event will be September 10th. We'll have speakers from around the world joining us every other week while we have these remote virtual evening under the stars. The talks are intended to be appropriate for all ages and interests. And at the conclusion of the talks, we'll have a question and answer period, followed by a guided tour of the night sky with our telescope. Now, tonight is not cooperating, and so we'll have to encourage you to come back in 2 weeks, and hopefully the weather will cooperate in 2 weeks. But we will be able to show you our campus telescope remotely and virtually, and show you what it looks like and tell you some fun facts about it. Picture of our observatory. It's located on top of Research Hall, George Mason University Fairfax campus. And then there's a control room in the building indicated by the arrow where we can control the telescope with a computer. Shown around the perimeter here are some of the images that have been taken with our campus telescope over the all by students since it was first built and since the telescope was installed just under 10 years ago. Just to highlight one of the recent pictures, we have a composite color image here taken by George Mason undergraduate Michael Reif with our campus telescope. Composite color image made with blue, green, and red filters. And what's really cool about this tail, which does have a reddish appearance, is that you can see a little streak, a dark streak in the tail. And that streak is actually the shadow of the coma and nucleus of the comet on its tail. And this was actually taken when the comet was moving away from the sun. What you may know or may not know is that the comet of a tail always points away from the sun, and that's why the shadow is cast on the tail of the comet. The tail doesn't follow the direction the comet is going. It's really the gas and dust getting ablated from the surface of the comet. We also have a monthly newsletter. Next of our newsletter is actually going out tomorrow. It's free. Please feel free to sign up. We cover interesting facts about latest updates on crewed space and robotic space exploration. We have highlights of our students and research. We talk about upcoming celestial events in the sky and more. So you can sign up for that also at science.gmu.edu/observatory. It's called the Mason Observatory Outreach Newsletter. Very convenient that it happens monthly. The word month that has its origins tied to the moon have similar durations. We also have a philanthropic organization called Patrons Observatory. If you're a student here at Mason, we have a club called Friends of the Observatory, which is free to join, and I encourage you all to search for FOTO, F-O-T-O, on the student clubs. If you're not a student, you're also welcome to join the Patrons of the Observatory. And in order to continue and inspire excellence in astronomy, as well as engage the broader Washington, D.C. area and community about the wonders of our universe, we need your help. And you can become a distinguished group, join a distinguished group of philanthropists. I'm having emphasis problems with the syllables today. It's been a long week. And your donations are tax deductible. And our entry-level membership is $50 per year to be a star member of the Patrons of the Observatory. And I'd like to thank our big members and supernova donors, as well as our new Nova Cluster and Star members over the past month. And thank you for your support. As I mentioned, I'm Professor Peter Plafchan. That's a lot of P's in a row, and I'm the director. My middle name is also P. And we have a new deputy director, Professor Rob Parks, who our speaker tonight might know and remember. He
Oh,
just joined our faculty this we have two observatory assistants, observatory TAs on with us tonight, graduate students Justin Wittrock and William Matsko. They will be helping us with the telescope tour tonight, at the conclusion of tonight's talk. And I'd just like to mention Brandon Iverson, who's a student at George Mason and president of our student club, as well as our tour guides. So we have over 1,000 students come through the observatory every year. And we have graduate and undergraduate students who conduct those tours, and you'll get to meet some of them over the coming public nights and evenings of the stars as they. Once again, feel free to follow us on Twitter, and if you have any more questions or would like more information. It is my pleasure tonight to introduce Dr. Angelle Tanner, an associate professor at Mississippi State University, Physics and Astronomy Department. Her research involves exoplanet surveys utilizing a variety of techniques, and she's been a member of the Kepler Participating Scientist Program and is currently a Kavli Fellow. She earned her BS degree from the University of Arizona and her PhD from UCLA, where we first met, where we were graduate students together, and we also worked together as postdoctoral scholars at Caltech. And it's been a pleasure to know and collaborate with Dr. Tanner throughout my career. She is the current director of the MSU Hollow Observatory and is the brain of the online Starchive database. She's given presentations at Star Trek conventions, Dragon has appeared in sci-fi and astronomy documentaries, and one day she hopes her research will not only the discovery of another potentially habitable planet around another star, also discover signs of life on that planet. So without further ado, I will turn it over to Dr. Tanner. Dr. Tanner, you can start sharing your screen.
yes. How do I, there we go. And now I share my screen. Thank you for that lovely introduction. It's been a pleasure. The pleasure's been mutual. And today I'll actually talk about, since I knew that Dr. Plavchin, he's also an exoplanet researcher, I figured I'd talk about something a little bit different, which is the work that I did as a graduate student at UCLA. And that was on the Galactic Center. I'm trying to, Peter, are you seeing my participant thing? Do I need to get rid of that too?
Yeah, we can see it just fine. And I know some of my students are very appreciative to hear something else besides exoplanets. So I'm excited to hear about your research on the Galactic Center.
Yeah. All right, so I'll just keep the participant list on here if that's can't quite get it to minimize. Go away.
Right. Yeah, we don't see the participant list on your screen.
You don't?
We just see your slides.
The whole screen. Yep. Excellent. Okay, so when I did whenever I arrived at UCLA in 1996, it seems like a long time ago, extrasolar planets were just barely starting to be a topic of interest. Some of the first extrasolar planets were announced in 1995 or 1993, depending on what type of planets you're talking about. But definitely, since I was a little kid, I was always interested in black holes. And so I went to UCLA, and then one of the biggest experts on the black hole at the center of our galaxy, Dr. Andrea Ghez, is at UCLA. And so I got involved in her research group. And we just celebrated the 25th year of doing research at UCLA of the Galactic Center. We had a little 2-hour celebration virtually, of course. I got sent some really cool chocolates, and it was pretty cool to do some reminiscing. So that kind of naturally led to me wanting to talk about the research that we did and what's been going on since I left and what's in the future. So first, we're going to do a nice little tour. I'm going to take you on to a journey to the center of the galaxy. I had to go send someone in my office. I haven't been in my office very much since March. So I sent someone into my office and go take a picture of this magazine because I couldn't find it online. But this is an article I actually got published in Sky and Telescope. I'm very proud of this, back in 2003. So let us go on a journey to the center of the galaxy. So here's an image of the Milky Way. We are here. The sun is about 2/3 of the way out from the center, or the nucleus, or the very center of our Milky Way galaxy. Let's see, I'm looking at my notes. There we go. So we are actually inside of the Milky Way. So whenever you look out into the night sky, you see this beautiful band of stars and dust and gas that is the Milky Way. Especially maybe not where you guys are, because you got a lot of light pollution. Even out here, it's very humid. But this picture was taken, it looks like the painted desert, it looks like the Badlands, maybe. But this is a very dry location, and of course the shutter got left open for a while, so you very nicely can see the band of the Milky Way going across the sky. And this direction is towards the center of our galaxy. I can kind of tell because it is very near the constellation Sagittarius. You'll hear that word a lot today, Sagittarius. And Sagittarius, it looks a lot like a teapot. There's the handle, there's the top, there's the spout. And as we zoom in to this part of the sky, so we're going to keep zooming in and zooming in. Here's another image towards the Galactic Center. Now Sagittarius, the teapot, is outlined. There's a bright part. There is a higher density of stars towards the Galactic Center, and kind of a bulge, we call it. And there's an opening called Bod's window. So that's the bright part you saw in the previous picture. But the Galactic Center is actually right about here in this annotated image. And you can see this is actually a very nice part of the sky if you have some binoculars, or maybe your observatory might train on a better night, train its telescope on some of these objects. It's actually a pretty good part of the sky to see some nice nebulae and everything. A lot of Messier objects in the area. But you can also see that there's a lot of some dust here, some clumps. And so that is indeed dust that is between us and the Milky Way, in the center of the Milky Way. So that means that astronomers, we aren't really able to use an optical telescope to study the galactic center. We tend to have to go and use infrared detectors and look at an infrared light, which is a longer wavelength of light than what we see with our eyes. So this image, this is an image taken by the 2-mass survey towards also the galactic center. It's a little bit of a smaller part of the sky. And here towards this bright blob in the center is more the galactic center. But you can see here that you can still see some dark clumps of material. These are the densest part of the dust. So the infrared light's not even making it out of these parts of clouds towards the center of the galaxy. So we do most of our work in the infrared. Let's go ahead and zoom in a little bit more. So, and that, well, that gives you a sense of scale of what part of the sky this infrared picture came from. Because when it comes to the galactic center, it's kind of hard to get a sense of scale because there's so many different images that have been taken. Now, one recent picture that came out of the center of the galaxy was taken at radio wavelengths. So now there's a new survey called Meerkat that took an absolutely gorgeous picture of this part of the sky at radio wavelengths. So radio wavelengths, they tend to be big arrays. Like I'll show you some data from the Very Large Array in Socorro, New Mexico. And so to scale, this Meerkat survey took a radio image of a box about this big, and it got this image. And you can see it looks a lot different than what we see at optical wavelengths. And we're going to zoom in on that a little bit. And you can see all this weird stuff going on towards the center of the galaxy. These roundish things over here on the edge, those are all supernova remnants. So those are stars, they're massive stars that exploded and went supernova. And these are the leftover debris from the explosion of those supernova remnants. So whenever you look at the sky at different wavelengths, you're detecting different physical phenomena that are going on. So this is hot gas left over from these supernova remnants. Now these, you're not seeing things, these weird skinny needle-like objects are magnetic filaments that are permeating out of the center of the galaxy. So our entire galaxy has a magnetic field. You're probably used to magnets, of course, that you might have on your fridge. Our sun has a magnetic field. That's why we get sunspots. All stars, many stars have magnetic fields. Well, believe it or not, the entire galaxy has a magnetic field. And so this is gas that's getting accelerated along magnetic field lines along in the entire galaxy. And if I go back, now this is a huge phenomenon. These are filaments that are extending thousands of light years across. So it's kind of crazy, the sense of scale that we have here. Now I go to the radio on purpose as well, because very early on, with some of the earliest radio telescopes, the area of Sagittarius was distinctive at radio wavelengths. It was so distinctive, there are just a few very strong radio sources in the sky. The sun is a well-known radio source. There is a galaxy called Centaurus, and it's now called Centaurus A. It's a well-known radio source. And Sagittarius, they knew there was something going on that was producing radio wavelengths towards the center, what we thought was the center of the galaxy. And then they called that Sagittarius A. Oops, oh, that advances my slides apparently. So now I've taken the picture and I've tilted it over, and then it's kind of, again, with many astronomical images, it's hard to show everything at once, because in the Meerkat image, it probably has pretty good resolution, but the way they showed it, they kind of overexposed the center part. So now we're going to zoom in to the square here at Sag A star. We're going to start getting smaller and smaller, and we're going to look at some VLA data that was taken in the 90s, and that's what this blue image is over here. And it has pretty good spatial resolution as well. It can see a lot of details. You can kind of tell it's an old image just by the crustiness of the picture. I think when they made, whenever they made the image, even just saving as a JPEG, it wasn't as high resolution as we have now. But whenever we took this data with the VLA back in the early 90s, now we're starting to talk about the history. We noticed that there's a very compact now radio source still towards the in Sagittarius A, and it got called, because we're clever with our namings, Sagittarius A star. So it's that white blob towards the center. And so we knew in the early 90s that something weird was going on at the center of our galaxy. So here's another, I'd never seen this picture before. This is beautiful. This is actually a composite image of, also taken with radio wavelengths, but then they also aligned and included some Hubble data and some Spitzer Space Telescope data as well. So in the radio, you're seeing a lot of hot gas and some magnetic fields that are causing some of the radio emission. And then whenever you include that with Hubble data, you can actually see where the stars are. And Sagittarius A star is still here. It's that white center towards the middle. And we're going to zoom in again. Oh, and this whole structure, I should say, it's on the slide, but this whole structure got named the Mini-Spiral. So it definitely has some spiral shapes to it. Similar, it's all related. Similar to hurricanes, similar to galaxies. All very similar physics. So now we're going to zoom in again. And this is an amazing image of what we call the central few parsecs. And sometimes we talk about light years with the galactic kind of, that's a unit that astronomers like to use. This is all, the Galactic Center is about a little more than 26,000 light years away. But whenever the astronomers, we tend to use the term, the distance scale parsecs a little bit more than we do light years. And it's like a factor of 3 between the two. And I always forget which way it goes. So this area has been called the central few parsecs. And this image was taken with the Very Large Telescope, which is in Chile. And it's, again, in the infrared. You can see over here, there's still some dark clouds. It's not that there's no stars there, it's that the clouds are preventing the light from those stars to escape. But now we are looking even closer towards the location of this Sagittarius A radio emission. And so we're going to zoom in a little bit more. Now there's a freaking mosquito flying around my head. So here's another VLT image. I'll start doing all of our Keck images soon, but the VLT, they've made some really nice color images. And here we're seeing, this is a color image. So they've combined the data images, just like you can make a color image from red, green, and blue. We can also do that in the infrared. This is infrared, so we don't see these wavelengths with our eye, but we can still put together different wavelengths of light. And that kind of tells us what kind of stars we have and if there's dust and gas in the image. So this is a whole bunch of stars. We know Sagittarius, that radio source is towards this part of this image. We've actually been able to align the radio images and the optical images together. That was one of the most important things we did when I was a graduate student, was make that alignment. And then we have a bunch of stars. I stared at this same little cluster of stars called IRS 16 from 1995 till 2004, so I know it well. There's IRS 7, which is a red giant star. There's IRS 3, which is a dust enshrouded star. And you see some red stars here, which I'll talk about later, because that was actually my thesis. And this structure, but you can also see some emission kind of in the background, and that's some dust, some more dust lanes that exist towards the Galactic Center. But all of our focus right now is towards, it's like you keep squinting and you see that there's kind of something towards the center of the image. And so we'll keep zooming in a little bit more. And it's the same image. I just included this other image here. This is the radio image now. And so you can see the little cluster of stars. Focus on this pattern of the IRS 16 stars here. That's the same as this pattern here. And even by eye, this is the big radio source seen in the radio data. And if you kind of look, if you blink back and forth between the two, you can definitely tell that that radio emission is coming from that part of the sky. And we zoom in again. And so now we're looking, this is about as small as we get. Actually, we zoom in a little bit more. We're going to eventually just focus on this cluster of stars here. But already we have zoomed in from whenever we started with that image of just looking at Sagittarius. Sagittarius is a few degrees across. So the moon is a half a degree across. And now we are talking about a part of the sky which is 5 arc seconds across. So there are 60 arc minutes in a degree. There are 60 arc seconds in an arc minute. So there's 3,600 arc seconds in a degree. And after all that math, basically I estimated that this field of view is 0.1% of the width of the moon. And a way to get a physical feel for that is go take a grain of salt and place it on your finger and hold it at arm's length and look up to the sky. And the part of the sky that we are looking at is about as big as that grain of sand. Tiny, tiny, tiny part of the sky. But yet so much going on. Okay, so in the early 90s, this image is taken a little bit later, but in the early 90s, folks at UCLA and also in another group in Germany, I'll refer to them as the Germans, maybe later on, we noticed there was clearly a little cluster of stars right about here. And so Andrea Ghez and some of her very first students, she had just started at UCLA in the early 90s, started focusing a lot of their attention on looking at the stars that are at this location of Sgr A star. Now at UCLA, we have access to the Keck telescopes, which are at Mauna Kea. They still are. They also had just come online in the early 90s. They, at the time, were some of the biggest telescopes in the world. They still kind of are, depending on who you ask. And so I was very lucky to, as a graduate student, to be able to go to Mauna Kea, another zoom in, and use these telescopes. So I'm going to embarrass myself with some old pictures. And I think this is one of the earliest trips I took. Based on there being snow. In fact, I realized this is probably not the trip that we took to observe the Galactic Center, because Sagittarius is only up during the summer. So I think this is actually a trip that I took in December with Dr. Plavchin and our friend Jenny Patience. She took me to the telescope that Dr. Plavchin uses right now. We were using IRTF, Peter, I think this was my first visit to the summit. But this is the Keck telescope in the background. Luckily, for the IRTF run that we had here, I actually had to stay at Mauna Kea. The top of Mauna Kea is at 14,000 feet. It's not the healthiest of places to be. The air is pretty thin. Luckily, I did not get altitude sickness. So they don't really, it's better not to be at the summit. So, and I'm complaining sarcastically. So they unfortunately, sarcastic, we have to actually observe from the headquarters, which is in Waimea, the beautiful little town of Waimea. This is the Keck headquarters. We did have internet in 1998. It wasn't as good as it is now, so we could actually run the telescopes from the headquarters in Waimea. There is someone physically at the telescope all the time, because if something breaks, the telescope operator has to go and actually physically touch things. I like showing these pictures because hydrangeas are some of my favorite flowers. And these hydrangeas at headquarters, because Hawaii, the weather is exactly the same year round. So no matter when you go to headquarters in Waimea, there's just these beautiful, gigantic hydrangea bushes that are there all the time. And again, like I said, totally sucks to have to go here all the time. Sarcastically, being one of those beautiful places on the planet. Okay, here's a picture of me working at the telescope. Look at the, this is a CRT screen. This is a Sun Microsystems computer. They don't even make this computer anymore. But this is what we did. I mean, a lot of the students appreciate this, real astronomers. We basically stare at computer screens and we write code. So we had to analyze the data on the fly. And I'll show you some of that soon. Now the student has become the teacher. And here's a picture of me with my two students, Claire and Fari. Last time we went and visited Mauna Kea. I think we're actually standing in front of Keck because we had been given a tour of the Keck telescope. So Keck is in front of us, behind the person who took the picture. I think I've been to Hawaii about 20 times now. Again, it totally sucks. Okay, so another thing that happened at the beginning of the early 90s was the invention of, well, we started off using something called speckle imaging, and I'll show you that in a second. But another important thing was the invention of something called adaptive optics. So some of you, of course, you've heard of the Hubble Space Telescope, and it is a lovely telescope. It's 2.4 meters in size, and it's in space for a reason, and that's because the Earth's atmosphere makes stars twinkle, and whenever you're looking at a star, a part of the sky for a very long time, it basically makes that image very blurry. So whenever we, in this case, whenever we turn adaptive optics off, that's what we would see towards Sagittarius A star if we didn't have adaptive optics. Adaptive optics is some extra mechanics that get built into these new telescopes that allow us to measure the way that the sky is twinkling and model that effect, and then basically give us a sharper image. And that's been key here. So it was the advent of adaptive optics at this time, and also the fact that the Keck telescope came online, which was important. So starting at around 1994, I think, a couple years before I started working with Andrea, they started getting images of this cluster of stars that were at the location of Sagittarius A star. They knew that that Sagittarius A star was right about here. And so what we did for many, many years is we kept going back every year, even twice a year, and getting pictures of this cluster of stars. And here's what we've seen after all these years. Hopefully it starts. I think if I click again, here we go. So this is kind of a recreation. It's a model of what's going on. But what was really exciting about doing this at the beginning is that whenever the first couple years, we noticed that stars were moving, but we didn't know if they were going to necessarily be orbiting. They could have just been passing by. See if I get the thing to work again. So over here is the year in the corner. And so over the years, we were able to realize that indeed, a lot of these stars were actually orbiting around something that we couldn't see with the telescope, with the infrared light. The most famous one is the star that you'll hear a lot about tonight called SO2. And this star orbits around Sagittarius A star every 16 years. So we're looking at something that it's orbiting every 16 years, and it's 26,000 light years away. It's insane. And so using Kepler's laws, the same laws that we use to talk about the planets in our solar system, the same Kepler's laws that we use to talk about extrasolar planets, we can use Kepler's laws to estimate the mass of the thing that these stars are orbiting. And it ends up having 2.6 million times the mass of the sun. And it's really massive, and you can't see it, so it's a black hole. It's a supermassive black hole. So that was pretty cool. And for these first few years, this is one of the original papers that got published in the year 2000. It actually took us a while. We had to convince some people, some disbelievers, which is part of science, that this indeed was a black hole. Some folks said it could have been a boson ball. I don't even know what that is. So Dr. Gez is a very, very bright professor. Literally, she's had a Genius Grant, and yeah, the group did an excellent job putting forth all the evidence and eliminating all the possibilities. And this is indeed a supermassive black hole. So it is supermassive in that it's 2.6 million times the mass of the sun. So it's not the remnant of a single star. It's about 26,000 light years away, and its size, or the diameter of its Schwarzschild radius, which we also call the event horizon in the movies, is about 0.2 astronomical units across, which is half the distance from Mercury to the sun. So it's a black hole that's bigger. The event horizon is bigger than the sun. So it all scales. It's all fun physics. But that didn't stop us studying it. So this is kind of cool. This is showing us the changes in the data that we've been collecting of this little star cluster. So whenever I was doing the work, 95 to about 2003, we weren't using adaptive optics. The Keck telescope didn't have an AO system on it yet. Andrea was very clever, and she used something called speckle imaging. She used to call it, actually she even called it poor man's speckle, and you can probably call it poor people's, well, that's not a good way to say it, poor man's adaptive optics. And so we had to take a bunch of images of the sky and put them and stack them all together. In order to get an image of the central cluster, it would take us about 4 hours. It would take me probably, after we were done taking data, it would take me 4 or 5 hours running the code on about 6 different computers. I was doing parallel computer processing before that was a thing. It would take me 6 hours to reduce the data, and I'd have to do that after, on the first night we'd collect the data, and I'd have to spend all this time reducing it. I was very tired by the next morning. All the professors went to bed, and I stayed up and reduced the data. And then later on, after I graduated, they started using the adaptive optics system. And then I think they still had to get a lot of data, but I don't think they had to take quite as long to reduce it. And so it only took 2.6 hours. And now the current system they use is called the Laser Guide Star Adaptive Optics. And I'll show you a picture of that in a second. And they're able to get this insanely beautiful image in 8 minutes. So we've gone from 4 hours plus 6 hours of crunching data to 8 minutes. And I bet it probably takes them about 10 minutes to reduce the data. I'm not bitter at all, no. But an absolutely gorgeous image. And you can see in all these images that you can see more stars, and it also helps them get more precise values of where the stars are to be able to measure more and more orbits. We just started with SO2. We had like a handful of stars that we were tracking, and now they have hundreds of stars that they're tracking. Here's an image. The UCLA group has absolutely no problem getting time on the Keck telescopes because these discoveries have been a pretty big deal. And now they've taken over both telescopes, and they're both aiming lasers towards the Galactic Center. This is pretty darn cool. I highly recommend, I didn't download any of these, but I highly recommend downloading some of the videos. It looks like a space war whenever they have these lasers on. You can't actually see them with the naked eye. They're not quite as bright. This, of course, this particular image was exposed for a while, but it is pretty darn cool. And you can tell, look, you can even kind of squint, tilt your head, and this is Sagittarius, so I can definitely tell they were looking towards the Galactic Center, and you can even tell that it's definitely right there in the middle of that dust cloud. That's pretty cool. So that was a big deal sort of in the turn of the last century. God, I can't believe I can say that. It seems like that was so long ago. But since then, I've also was able to help them get some of the first spectra of the stars, of SO2, for instance. So we take the light of the star and we look at it at multiple wavelengths. And that's important for 2 reasons. One, just looking at the motion of the stars on the plane of the sky, you don't get the full 3-dimensional image, 3-dimensional orbit. There's a little extra math, that's some ambiguity. Mother Nature is not going to let us have it that easy. And so if you're able to measure the velocity of the star as well as it's moving around the black hole, once you get that information, you can actually get a full 3-dimensional orbit. And you can do that by the redshift and blue shift, or the Doppler shift of the lines that we see that are being produced. I mean, the signal to noise, as we call it, of this spectrum is horrible compared to what they're getting now. The improvements are insane, but that little bitty dip right here is actually due to hydrogen, it's a bracket gamma line, in the atmosphere of the star. And because we know what different elements are in the atmosphere of the star, and we know the color of the star now, we know that this is a B star. Oh, be a fine guy or girl, kiss me, which is a very un-PC term now that we use. I gotta find a new one. This tells us this is a B star. We also call these early type stars. So this is a very young star, and it's a very massive star compared to the sun. And so now that they were able to measure the velocity, they were able to make a cartoon of the three-dimensional orbits of all these stars. So it's like they're like it's like a bunch of bees buzzing around the black hole. Kind of a random set of orbits. Not so random, but random in this picture. And then we also have been studying some of the clusters around the galactic center, the quintuplet cluster. There's a very famous star in the area called the Pistol Star. I think it looks like a crawfish. I do not know why they called it the Pistol Star. It was kind of dumb. And the Arches cluster. And this is important because these clusters and the fact that the SO2 star is a B star tells us something about how stars form in this weird environment. So we have these are young stars compared to the sun. They're only a few million of years old, but they're forming in vicinity of a black hole. And it turns out that does impact the type of stars that get formed. Most of the stars that get formed tend to be more massive than the sun. So that's already telling us some of the astrophysics that's going on. Now, I can't talk about all this without mentioning my thesis just a little bit. While Dr. Gez was focusing on all the stars orbiting around Sgr A Star, I was always asking for them to pretty please just look right over here at these objects, IRS 10 West, 1 West, 21, and 2. And these are interesting, and the reason I think this is why she gave me the project, is IRS 21, it's weird because it's actually resolved. It's big. It's physically very large. It's a couple thousand, if I remember my own thesis correctly, astronomical units across. Stars aren't that big. So there's something weird that was going on with IRS 21. And it's the closest to Sgr A Star, so it often would be in the field of view. You could tell that it looked different than the other stars. And then I went and looked at these other stars over here, 10 West and 1 West, and then I did some fancy image reduction, and I noticed that all of these stars had these weird horseshoe shapes around them, and it turns out that they're bow shocks. So what's going on is this mid-infrared image is showing dust. The dust this is a river. This northern arm is a river of dust that is, well, slowly in astronomical terms, flowing in to the black hole. And these are like pebbles in the stream, and that they make these bow shocks as the material flows in towards the black hole. And that was my thesis. The black hole burps. So they've been monitoring light coming from the black hole now that we know roughly where it is. And over the years, once they were able to get much better data, they were able to notice that it does indeed emit some light in the infrared. And they think it's material falling into the black hole. So when it eats, it does actually burp a little bit. And it gives off, that's a fun term for saying it gives off radiation. This became a big deal a couple of years ago because there was a blob that they then named a G2 that was heading straight towards Sgr A Star. They've been tracking all these stars, and there's one heading straight for the black hole. And it was definitely kind of blobby. So here it is over here. And notice all these stars are mostly round. You have to be a little careful because the Earth's atmosphere still plays tricks on us. So they noticed that this blob over here in 2012 was heading straight towards the black hole. They thought that because it was not quite circular, that it could be a dust cloud. And so that kind of made the news. They got lots of telescope time. And then they actually watched it as it passed right near Sgr A Star, and it survived. So they were all placing bets, I'm sure, at UCLA and in Germany about whether or not they were going to see this blob. And the fact that it did survive makes us actually wonder what it really is. I think one of the theories now is it might actually be a binary star as opposed to a gas cloud because if it had just been a gas cloud, it would have gotten ripped apart by the black hole. In even more recent years, so SO2 has been a big focus of a lot of study because it does have an orbit that's actually small in time compared to like other astronomical things that take millions of years. And now that we had an orbit, we knew when SO2 was going to make its closest approach again to the black hole. And the UCLA group, they're very interested in understanding the physics of how light from the star would get affected by passing so close to a gravitational field. Now we're starting to talk about Einstein, and this is all general relativity. And one of the predictions is that as a star passes very near the black hole, it's affected by the gravitational force of the black hole, and its light would get redshifted. And that's called a gravitational redshift. And the way I think about that is I used to go skiing when I lived in California. It sounds weird, but it's true. There's actually skiing places not that far from LA. And when it snows, sometimes you get these little divots near the trees. And if you ski too close to the trees, you'll get stuck in these divots. And I did all the time. And I would get stuck in a divot and I would try to climb out of the divot. And as I climbed out of the divot, I would lose energy because I'd be tired. So you can imagine as in general relativity, space-time is warped and the black hole is producing a huge divot in space-time. And as the star passes close to the black hole, the light from that star has to climb out of the gravitational well near the black hole. And when it's climbing out of the well, it's also losing energy. And whenever light loses energy, it becomes red. So it's actually a pretty nice analogy. So this was predicted. Many of Einstein's theories, general relativity was predicted and confirmed 100 years ago. But this is studying, are his predictions applicable to a supermassive black hole? And this is kind of a unique thing to predict. And sure enough, the data that they've taken, they were able to, Einstein had it really, he had it on, he was right on. So it's pretty cool. That happened just a few years ago. And that was something actually in the picture that I showed of me and my students at Keck, that was the GES group, that's what they call themselves. They were actually at Keck during the summer. They were doing some writing, but they were there to take data because it was 2018. They were collecting the data to make this prediction to prove that this actually happened. Now, even more recently, we've noticed that there wasn't really a good figure for this in the papers, but another prediction of GR, what happened? Did I crash? What happened? Oh, I don't know what happened. Okay, good.
We can still see your screen.
Okay, that was weird. I'm not touching anything. Oh, I know what I did. I touched the link. I don't know why those links get saved. Go away. Another prediction of GR would be the precession of the orbit of SO2. The orbit of Mercury precesses due to the gravitational influence of the sun. And so this is completely analogous to that. And I'll just tell you that a paper just came out a few months ago where this was not the UCLA group. This was the group over in Germany, where they've convinced themselves that they're seeing the orbit of SO2 actually precess as predicted by general relativity. So that's kind of a big deal. Another star in the area has been made news just a couple weeks ago, another influence to give this talk. Almost one of my last slides. And this is SO102. And let's see, here's the orbit of SO2 over here in orange. And then because the data has gotten so good, they're detecting even fainter stars. SO2 has an orbit of 16 years, and SO102, I think I saw in the paper, has an orbit of 11 years, so it's going even faster. And then they just said that whenever they measured it going probably its closest approach towards the black hole, that it was moving at 8% the speed of light, which is fast, as you might appreciate. So that made the Bad Astronomy blog. This is one of our buddies, Phil Platt, who talked about that. So there's still lots of very exciting things going on at the Galactic Center 25 years later. So what's next? So there's a new generation of telescopes being built. The one that UCLA will have access to is the 30-meter telescope. In case you didn't know, it's 30 meters in size. And the Galactic Center group is on it. Here's what they're doing right now with adaptive optics. I think this is supposed to say laser adaptive optics. Here's what they're doing kind of now with the laser adaptive optics. And then once we get a bigger telescope, we'll see this many more stars. And if you just stare at that, that's a lot of stars. It's really cool. And I went ahead and I looked over their white paper. They're basically, I mean, they're going to be able to find stars that are even closer to the black hole. So they're going to further be able to study the unique environment of what physics is going on so close to a gigantic black hole. So it's pretty neat stuff. And here's just one of the images from the press. Wow. That's a lot of stars. It's amazing. And then finally, this has been an image this was an image that popped out in the news a couple of years ago of the first direct image of the event horizon of a black hole that was taken with the aptly named Event Horizon Telescope. It is an array of telescopes all over the world. Now, the image that hit the news and became super famous was not of the center of our galaxy. It was actually an image of the center of M87. M87 is further away. It's another galaxy, but its black hole is a billion times the mass of the sun. So ours is a couple million, it's a few billion, and that factor of 1,000 kind of makes up for the fact that it's further away. And with M87, we don't have all that dust and gas between us and it. So they were able to get the data, and it took them a few years to get it, and crunch, and then became the meme-worthy image of the first image of the event horizon. I can tell you that they collected data for Sgr. When I Googled it today, unfortunately, it looks like they got hit with COVID too, because they needed to collect some more data, and of course they haven't been able to do so with all the observatories being shut down. But keep an eye out for this image, because I'm assuming something might come out in the next couple of years. It's really complicated. I'm not familiar with the real true logistics of how they combine the data. I just know that it takes supercomputers and that they use many radio telescopes or millimeter telescopes as well all over the world. And with that is it. Thank you very much, guys. Folks. That's pretty good. All right, good. I was a little worried when I realized it was supposed to be 30 minutes. I'm like, oh, oops.
Thank you, Tanner. Dr. Tanner, that's a wonderful talk. It's a trip down memory lane.
I know. And I actually made this image, this background image, I made this with a computer graphic thing back because we had so much time when we were grad students, huh?
Yeah.
But yeah, once I started realizing I was going to have to start writing code, I realized this was just work, so I stopped. But I did make one pretty picture showing everything.
Well, thank you, Dr. Tanner. As a host privilege, it's interesting. I think we switched roles. When I was an undergraduate, one of my very first projects was working with the Merlin camera. And I didn't take the data that you referred to in your talk when it was on Keck.
Oh, okay.
But I got to collect and analyze the data when Merlin was on IRTF.
Oh, okay.
And
You know what's really sad is that Merlin data never got published.
the
And
Keck data?
not the Merlin data. No, and you and I can talk about that offline.
Yeah, sure. So I collected, actually it wasn't IRTF data specifically, but it was Palomar data. And I had an entire summer analyzing that data and doing what's called deconvolution. And
Yeah, I did that too. Yep.
and the image I got was pretty good, but the Keck data was better instantly. And I was like, oh, I'm obsolete now. Like a year later.
5 times bigger, but yeah.
Yeah, so we're gonna now start taking some audience questions.
Please.
And if you have a question in the, please post it in the chat, and I will ask our speaker tonight those questions. So the very first question came from Alex, and Alex is still on the line. At the very beginning of the talk, they asked, and I presume this is in response to black holes, but deadly. Maybe it was magnetic fields, so I'm not quite sure, but we could probably answer both questions.
Was it? I'm sorry. Was that? Are they deadly?
Oh, is it specifically in reference to magnetic bursts?
Are the magnetic bursts deadly?
Yes.
Is 8 Gauss deadly? I think isn't that pretty high? I think it's a pretty high magnetic field.
Speaking from experience, if you happen to have an implanted device like a pacemaker or defibrillator, you can't go by nearby very strong magnetic fields.
Oh,
and
you know it in Gauss?
Yeah, so
how strong a Gauss is.
Yeah, I don't know the answer to that question. Magnetic field strength is deadly. I'll look.
I mean, it's got to be. I mean, if you scale it up, although I guess if it's diffuse, that'd be a good question for Cornelia.
Yeah, so a few tenths of a Tesla can be lethal to people with certain kinds of prosthetics, aka implanted devices, or perhaps like
Hey, one of Peter's students, convert 8 Gauss to Tesla, please.
I think it's, let me actually.
I don't want to yell at Google right now because that would be weird.
Yeah, so 1 Tesla is 10,000 Gauss. And so what was the number you were quoting?
8 Gauss, I thought.
8 Gauss. So it sounds like that's still safe for humans.
It might be just so diffuse, even though it's huge.
Yeah. No, that's a great question. Thank you, Alex. Question. He's going to dance. He's going to dunce now. No, you're not a dunce. That's a good question. I didn't even know the answer to it. I had to look it up.
We're done.
Yes, and the Earth's magnetic field is much weaker. Thank you, Miss Berlin. So next question we had during the talk was from David, and you actually answered it a little bit later in your talk, but just to reiterate, is there any glow from the black hole? And sometimes there's a bit of confusion about, aren't black holes black? How do we get a glow from them? So I'll just add on to that question a little bit. And
that's an excellent question. So what you're seeing, and you can kind of see it in my CGI image, I do have a little blob here that I put in. And what black holes, indeed, whenever you cross the event horizon, light cannot escape. But what you end up is you have a little, just like if you look at a drain, the drain of a sink, you have material falling around, you get what's called an accretion disk. And that accretion disk is extremely hot gas. So I didn't even show you guys an X-ray image because that's a whole different area. There's a lot of X-ray light coming from the Galactic Center too. And so you're seeing, you do the burping, what we think the burping is material that's falling into the black hole and it's getting heated up and enough that it produces infrared light, but we also see it burping in X-ray light too, and they see it burping at radio wavelengths. So you're seeing different physical processes that are producing different wavelengths of light as this material is getting stripped apart. I'm sure some of the stars do get ripped apart as they go in to the across the event horizon. So you're seeing a lot of that light in the accretion disk. Yeah, so a lot of black holes. In fact, most black holes that we know about in our galaxy were discovered as X-ray sources, like Cygnus X1. So it's the same phenomenon.
Okay, excellent. That's great. And we have another question. When you were showing, this comes from David Willens, what you showed the Event Horizon M87 picture, and they asked, is that an actual image or is there some artistic license there? And I think that question too, because we have actually two different images of black holes there. So maybe you want to speak to what we're looking at.
That's an excellent question and something I know about very well. So the image that I memed, that was memed, is the on the right is this is the actual image that the Event Horizon took. Now the image on the left, if you recognize it, and I had to make sure not to put a planet in there because there was a planet, is the image that was created and used in the movie Interstellar. Now, what's interesting about that image is that I used to play poker with Kip Thorne's students and his administrative assistant, and she kept bragging for years that they were working on this movie called Interstellar. And what was really amazing about the movie is that Kip Thorne, who is Mr. Black Hole, he's like the expert next to Einie. There's a few other people, but he actually worked with them, and they took his equations, and he was even on set, and put it into CGI. So while this is a CGI movie produced image that you saw in the movie, it is still the most physically accurate, we think, image of a black hole. So it's a wonderful question because it is the combination of science and science fiction. And so there's a wonderful, I can't even begin to explain why this image looks like this. There's a wonderful YouTube video of an individual who explains this. And even when I watched it 3 times, I had to think about it. Because there's some weird stuff going on over here with the warping of space-time. But yeah, so it's technically a CGI image, but it's the best one we've ever created of a black hole. So, excellent question.
Yeah, and what about that one on the lower cartoon?
What? This one?
Yeah, is that real?
Get the meme? Yeah, all these are. It's just the same one. It's copied and pasted.
Yeah, so that's the actual radio image.
Yeah, this is what the Event Horizon saw. I just take one of these now. Yeah, it looks like a donut. It looks like a donut. But this image also, the theorists that were working at the EHT, they produced a bunch of images of what they think we'd see, and this was actually what they actually did see was pretty darn close, just a lot more blurry because the telescope, we just don't have the ability optically to see better detail.
Okay, thank you, Dr. Tanner. So just to give you a brief update, if you want to give some claps for Dr. Tanner, there's a reaction option in Zoom. You can post some claps. I'll post some right now. There we go. There's some claps for our speaker. We have some more questions, so we'll continue with the questions. And we have a lot of thank yous for an excellent talk, Dr. Tanner, in the chat. So here's our next question from iPhone. When will the new 30-meter telescopes be online? That is a great question to ask a professional astronomer right now.
I defer that to Peter. No.
Oh boy, no, you're the speaker tonight. I will defer to you, but I can chime in later if you want.
Well, yeah. So this is a good question for the day and age that we are living in currently. So the Europeans, the Europeans like to outdo us in lots of ways. So they're building their own 30-meter telescope with, I don't know if it's 30 meters, Peter, I forget, the ELT. And
35. Yeah, they're just showing us up.
Is that in Chile? I think it's in Chile.
Yeah.
So we'll definitely have an ELT that's in the works. The thing is with the 30-meter telescope, and I actually see both sides of this because that's just me, is that the folks at Mauna Kea, there's been a little bit of controversy about putting it in Mauna Kea because it's a revered site for the local Hawaiians, and we have not been great to them in the past. So there have been some delays, and if you Google this, you'll see it all over the internet. So there's been some cultural / political delays I've actually not been hearing a lot about what's going on. We've definitely cleared off the sites. The current status I'm not quite aware of. I haven't really been getting a lot of emails from the TMT users group lately, Peter. And now we've got COVID, so I think everything's on Mauna. Well, no, Mauna Kea is open, right? Because we're getting data at the IRTF. So I think everything is kind of on hold right now, and they're dealing with some injunctions and stuff. So we're ready to build, but we need to work through, maybe have a few talks with ourselves and figure out whether or not we really should put on Mauna Kea, or we have some backup sites to put it in Chile and even Mexico. Yeah, so we'll see.
Yeah, it looks like the ELT in Chile will definitely be on Sky first sometime in the next 5 to 10 years, I think, will be first light. And
telescopes take a long time to build. It even takes a few years. Also, the Giant Magellan Telescope you should keep an eye out for.
Also going in Chile, yeah, and that's a 25-meter one. The U.S. decided to build 2 smaller ones, and then Europe is building 1 bigger one. And just to add a little bit onto that, you know, the events surrounding the 30-meter telescope construction has caused a lot of cognitive dissonance among professional astronomers, and the debate over the role that astronomers play in colonialism on Hawaiian lands. And there are definitely some good arguments on both sides. There's also some false arguments on both sides. Specifically, you know, claims that the damage to water supply are probably misplaced. But there are valid concerns about how the mountain has been managed, how many telescopes are up there currently, which is currently 12. And
we're decommissioning some of them too. So one of the things I think we've agreed to do is take down a couple and sort of, you know. And
yeah,
then,
not just a couple, 4.
4?
Yeah. And it's interesting. I have a hard time personally understanding what's forward. I see that there needs to be more engagement with the community in Hawaii, and there are differences of opinions in Hawaii. It's not a monolithic population in Hawaii, and there are people that support it and people that are against it, the construction as well. So fortunately, my research doesn't depend on the 30-meter telescope, and I'm a bit relieved that I don't have to worry about it. But I do hope there is a path forward for the telescope on Mauna Kea, because it literally is the best place on the surface of this to build that telescope, hands down.
Yeah, and plus we'd be missing half the sky if we don't have anything in the northern hemisphere. So there's also
right. So it'll be interesting to see. We have a comment in the chat from JP. I wish they'd put more on Lick Observatory, but I'm biased. Lick Observatory fortunately did not burn down last week. I don't know if you've been following the news, but Mount Hamilton. So for people that know, Lick Observatory is the oldest mountaintop observatory on the planet, constructed before electricity.
I was going to say,
around.
Don't be dissing Stonehenge. Yeah, okay.
Yeah, in the late 1800s, yeah, fortunately the only one structure was lost, and it was not an important structure, but there was a fire.
It was really close. I mean, people were staying up all night. Again, this is not the first time we've had to do this. People were staying up all night watching the cameras that were on, just watching the flames get closer and closer to the telescopes. We were very lucky. This almost happened to the telescopes on Mount Wilson in LA a few years ago.
Mm.
And Palomar too. I mean, Palomar had a really...
Yeah, I had an Australian colleague ask us, haven't you learned anything from the Australian fires? And really, the observatories are really in a funding decline in the US, and they had to make the tough decisions about keeping to operate and keeping to pay people's salaries versus spending the money to protect the observatories from future fires. And it looks like they made the decision not to clear it off, and that was a very risky decision to make. And I don't know what the future holds. It's going to be quite interesting. The next question we have, and by the way, stay tuned. We're going to have a closed dome tour with our campus coming up soon. I just wanted to say a few words about that. We had opened the telescope in anticipation of showing you Jupiter. We could actually see it for a few minutes during Dr. Tanner's talk. But unfortunately, the clouds rolled in and now there's precipitation coming in. So we had to close up. We just missed it by a few minutes, but we will be showing you that in a little bit. All right, we have, I think what we'll do is we have 2 more questions. The first one comes from Kia. What was the term of the river of dust that was flowing into the black hole?
The Northern Arm.
Northern Arm, okay. And the yeah. And the next question comes from Zachary Roberts. How do you calculate the Schwarzschild radius?
Oh my goodness, I do not have the equation. You Google a Schwarzschild radius calculator, which is what I did minutes before my talk. So isn't it just, Peter, isn't it mc squared is equal to 1/2 mv squared? Isn't it that, is it that easy? No, that's not, no, it's mc, it's 1/2 mv squared. Is, use Newton's laws. Newton's laws.
Yeah, I think you set the universal law of gravity equal to 1/2 mc squared.
I'm trying to do a derivation in my head.
Yeah, so it's g times the mass of the black hole divided by the Schwarzschild radius squared is equal to 1/2 c squared.
That makes sense.
But I think that's, of course, that's the classical approximation. The exact answer comes from Einstein's theory of general relativity, and a solution to that called the Schwarzschild metric. And there's a real fascinating story about Schwarzschild, who was killed in World War I when he was still making major advances in astronomy. Yeah, the equation I always remember is you take the mass of the black hole and multiply it by, in solar masses, and you multiply it by 3, and that's the event horizon size in kilometers. So a 3 solar mass black hole has a horizon radius of 9 kilometers. By the way, with all the children in Pokemon Go now, I think now is the time to switch to metric. My 6-year-old, he's talking. I heard him talking in kilometers today to his.
Oh, that is true. All of my, I'm looking at my Pokemon Go. It is all in kilometers, isn't it?
Oh, and we've got the equation there in the chat. Yeah, so that come from. Oh, that's okay. So the equation for the Schwarzschild radius. Thank you. It's proportional to the mass of the black hole. That's great. Yeah. Okay. Oh, it's a gravitational potential energy. I had the force. GMM over R. Yeah, sorry, not R squared. Okay, great. You can tell I don't do black hole stuff anymore. Last question.
Flashback Peter.
Comes from Anand, which is, how do you, I love this question. This is a good one. How do you think the Starlink satellites will affect future astronomy research telescopes? And Dr. Tanner, I'll let you take that question. I'll add some more at the end.
We were just talking about this yesterday in this conference I was at called .astro. In fact, the astronomers even made a song, which I won't play for you because it was kind of hard for the ears. So for this type of stuff, to be honest, for this, am I still sharing my screen? I am, it says that. So remember, this is a very, very, very tiny part of the sky. So we would have to be very unlucky for a Starlink to go through this particular field of view. However, we are building telescopes right now, the Vera Rubin telescope and other telescopes which have a much, much wider field, and they're doing different science. And the Vera Rubin telescope, its field of view is like a few full moons across. It's huge. And it's being built. I mean, we have spent what, billions of dollars on this telescope and these instruments. And it was, you know, these projects start like 10 years ago. They start 10, 15 years ago. They take a long time to get done. And unfortunately for these large surveys, the Starlinks are going to be a huge problem. And if you Google Starlink in astronomy, you'll see some images that people have already taken using other surveys, large-scale surveys that are online right now. It's also going to impact, I have to say, with NEOWISE having been in the news a lot lately, it's going to really impact amateur astronomy too, because there were definitely some Starlinks that photobombed some of the amateur astronomy pictures that were people are trying to get a pretty picture of the comet, and they got Starlinked. And some of the people are saying that, oh, you can take it out with the data. Not in all cases. I mean, the astronomers, we kind of know what we're doing when it comes to how we take our data. But one of the things, and Peter, if she has time, I'd highly recommend inviting Lucian Walkowitz to give a talk. She gave an excellent talk about Starlink during .astro, and they're selling it as a way to bring broadband internet to the world. And living in rural Mississippi, I 100% appreciate that. But once you actually start looking at how much it's going to cost the individual communities, it's not going to be cheap for the people that they're claiming it's going to be cheap for. So Lucy in her talk has got some excellent plots, and the astronomers got together and they put together some infographics that I think you're going to start seeing out there to counteract this discussion that we're going to be bringing internet to the masses. Because I 100% agree, especially during COVID. I have students in my class, there are students in K through 12 around Mississippi that are suffering, of course, because they don't have access to the right internet. Starlink isn't going to bring them internet the way you think it is. So you got to really kind of read between the lines. And this has also got some pros and cons, much like the Mauna Kea discussion. Go ahead, Peter.
I couldn't agree more. You know, with our campus telescope, we see satellite streaks more often on the images we take, and you summed it up nicely. SF has shown for the Vera Rubin telescope that about half of all images will be contaminated by commercial internet satellites if the full fleets are deployed. And I urge all of you on this call tonight, if you are interested in supporting astronomy from the ground and for the awe away from light pollution in the night sky. Astronomers can escape light pollution, right? But they can't escape the light pollution from satellites, no matter where you are on Earth. And to think that one billionaire's company in the United States could control the ruining of the natural beauty of the night sky for everyone on the planet.
Think of the cultural impact too.
We need to take some action. So please write to your congressional representatives, express your concern about the light pollution from commercial satellites when they're fully deployed. And we're going from maybe a couple thousand operational and active satellites to potentially 50,000 satellites. And they're particularly bright. So it's gonna have a massive negative impact on ground-based astronomy, and just take away that natural wonder of looking up in the night sky and seeing the twinkle of stars.
If that doesn't impact you, I mean, it's not going to do what they say it's going to do. So you just don't have to take
so Alex asked, who's the billionaire, and can we get out the guillotine? Not a guillotine. I think that's a little too antiquated. But it's Starlink is owned by Elon Musk, of course, and Jeff Bezos has his own plans for.
Bezos wants to do another one for Amazon.
Yeah, and there's others. OneWeb maybe went bankrupt. We'll see if it gets rescued. But there are other companies looking to do the same, and those are just two of the bigger ones. So with that, I'm now going to turn it over to our tour guides for the night, who are going to share their screen. Dr. Tanner, if you don't mind stopping your screen share, and they're going to share their screen and take over and view of our campus telescope and feel free to continue to ask questions, and we'll answer as we go.
Yeah.
Already on it.
Okay, thank you all. So I hope you enjoyed the excellent talk by Dr. Tanner. So as Peter said, we'll be giving you all a virtual tour of the observatory. So what's neat is that we can connect remotely to the observatory, and we can control the telescope from the comfort of our own homes, our own couches, and our own beds. Of course, that comes with some drawbacks. It's a little easier to fall asleep when you shouldn't. But Justin is sharing his screen right now. So what you're looking at is just the desktop of one of the computers that we have in the control room on the roof of Research Hall. So one of the things that makes it possible to do our remote observing is a set of cameras that we have at the observatory. So let me just pull these up right here. I'll just enlarge this. So we have three cameras in use right now. I'll just talk about them briefly one by one. So if we zoom in on this, this is the control room. We are currently connected to the computer that's in the left corner. You'll see we have another computer down here, which is a backup computer, essentially. It's a clone of this main computer that we use. And this backup computer is used for testing software and Windows updates. A few months ago, a Windows 10 update managed to break some drivers and rendered our telescope completely useless for a few months. So we had to wait until Windows 10 got their act together and released an update. So we disabled updates on that computer, and now we only test new software on that secondary computer to prevent stuff like that from happening again. But anyways, this is the small room where students and researchers spend the night collecting their data. So everything you really want to do could be done in this control room. So not much more to it than that. If we go to the next view, there's no signal camera. This camera is currently in a box, so we don't really expect a signal from it. Right here, it's a little hard to get a sense of scale since you don't really have a good reference here, but this is the dome that houses our telescope. So you can see the roof of Research Hall and the dome and whatnot. And I think I'll take this time to say that there's a couple of, there's two main activities that we do at the observatory. The first is research. So one of the things we do is exoplanet follow-ups. So this telescope is good for detecting exoplanets using the transit method, which is essentially a planet passing in front of the star. And that planet passing in front of the star will cause the light we receive from the star to dim a little bit. And it's very, very, very faint, but we can actually detect that dip in brightness with this telescope. So what we can do is point our telescope at a potential star and planet system, and we can just stare at it and see if we see what other missions have seen in regards to dips in brightness. So the other thing we do besides exoplanet research is outreach events such as this. As Peter said at the beginning of the talk, usually we like to have these in person, but unfortunately we gotta be virtual. So in addition to our Evening Under the Stars talks that are every other week, we also host some private events, which are mainly attended by Cub Scouts, Girl Scouts, Boy Scouts, and that. But we also have had marriage proposals here. So that was, you never know what you're gonna get, but pretty much anyone can schedule a private tour if you're interested. So those are the two main things we do at the observatory, exoplanet research and outreach. And if we go and take a look at this last image, this last camera right here, we are going inside this dome and we will be staring at our giant telescope, which is angled so it's pointing directly at one of the cameras we have inside the dome. So this particular telescope is 0.8 meters. So when people quote a size of their telescope, they're usually talking about the diameter of the primary mirror, which is that really round, shiny thing towards the back of the tube. So it's about 0.8 meters in diameter or 32 inches across. So this is a fairly large telescope, at least relatively speaking. It's one of the largest telescopes on the eastern seaboard, but even so, this is quite small compared to some of the largest telescopes in the world. The largest telescopes are about 10 meters in diameter. And as I said earlier, this is only one. So another thing that might be nice to know is this telescope, a lot of people overestimate how much something like this costs. A lot of common guesses are usually in the $1 million range or something like that. But turns out this telescope only costs a small sum of $300,000. And relatively speaking, that's not a lot of money for astronomical equipment. So the telescope was about $300,000. The dome that it's sitting in was about $80,000. And between 2017 and 2019, we put about $150,000 worth of upgrades into the telescope. So this telescope is a reflector telescope. So that shiny circle you're seeing towards the back of the tube is a mirror. So what's going to happen when light comes into the dome, it's going to go into the opening of the tube, and it's going to bounce off that big shiny mirror in the back, and then it's going to come up to this weird kind of almost the speakerphone looking thing. But that is actually the secondary mirror of the telescope that's about 1 foot in diameter. So light will bounce off the primary mirror, it'll go to the secondary mirror, and it will bounce again through a hole in the primary mirror. And from there, there is a third mirror that's a diagonal reflector, and it will channel the light into one of the 4 portholes we have on the back of the telescope. And attached to each one of those portholes, we have a different instrument that we use for astronomy or outreach. So, Justin, if you could go ahead and flip the telescope so we're looking at the instruments on the other side, that would be great. And while the telescope is moving and flipping over, if anyone has any questions so far, feel free to ask them in the chat. Doesn't look like there's any questions, but anyway.
We've got a question while Justin's slewing the telescope. I'll ask it for you, William, just so everybody can hear the question. It must be difficult to build a 30-meter telescope, and to say the least. Why not build many 10-meter telescopes instead? So what's the advantage of a really big telescope over a smaller telescope?
Well, the advantage of a really big telescope is really just that you can, at least in terms of optical telescopes, is that you can just gather more light. So it really is a case of bigger is better. Dr. Tanner earlier in her talk mentioned that you can link some telescopes together to form some larger telescopes. That's true, but you can only really do that with radio telescopes. You can't do that with optical telescopes. So when you have a bigger, like a 30-meter telescope, you're just significantly increasing the amount of light you can gather. And that enables you to make out finer details in objects, and you can also see fainter objects than you could otherwise.
If I may, you can actually combine telescopes in the infrared. That's called the Sgr array at Mount Wilson.
Oh, so yeah.
But you were right in that those, while you can get the better resolution, you can't see the fainter things. But yeah, so there are some instances where you can do infrared and optical interferometry, it's called.
Oh yeah. Sorry, I wasn't.
That's okay.
I had the Event Horizon Telescope in my mind. I wasn't thinking about infrared stuff. But anyways, looks like the telescope is still getting flipped over to look at the instruments we have. Looks like that's coming into view now. So if you could just turn it a little more, Justin. So anyways, the software that you're looking at now is something called the SkyX. It's what we use to control the telescope. So it's very much a point and click kind of system. We can just click at some point on the sky. Let me just pull it up again right quick. So what we're looking at here is a projection of our local night sky. And if we want to just click on something like...
Yeah, it's what we would see if it weren't so cloudy right now.
Yeah, that's what we would see if it wasn't so cloudy. So if we just click on a star, it'll tell us what it is, and we can literally just hit slew and it'll go to that star. So it's very convenient, and if we just don't know the location of something on the sky, we can just type the name of it into this box, and hopefully it's in the box. If not, we can just type in its coordinates. So this is definitely a very, very convenient system for us. It definitely beats moving the telescope by hand or some remote paddle. So anyways, let's go ahead and look at some of the instruments we have on the telescope. This is a pretty good view. The CCD is a little obscured, but let's start with this thing that's towards the upper left. It has these handles on it. So that right there is a spectrograph. That's the newest addition to the telescope. It isn't actually functioning yet, but the spectrograph is just going to take light and it's going to disperse it into its constituent components. So you can think of it kind of like a prism. If you pass white light through the prism, it'll break it into its constituent colors. So a similar kind of idea for spectrographs. So that will enable us to do some pretty neat spectroscopy. The other instrument we have to the right, you have this, you can't really tell the color, but it's a black rectangular box. And behind it is a smaller kind of square, and that is our CCD. It's the main camera that we use to take images of the night sky with. So this camera is a 4096 by 4096 pixel array, so it's about 17 million pixels, which is reasonably high res. We can cool this down to some nights, if it's not blistering hot out, we can get it to minus 30 Celsius, which is pretty cold. So this black box right here, this rectangle, is the filter wheel. So it holds a variety of filters, red, blue, visible, infrared, clear, H alpha. So we can look at the sky in a variety of wavelengths. So the other piece that we have, the porthole, the next porthole is actually empty. We usually have a near infrared camera on there, but that's away in maintenance limbo. And then lastly, we have an eyepiece on the telescope. So if you all were here in person, that's what you would be looking through. Well, not tonight since it's too cloudy. But yeah, so that's the telescope, our telescope in a nutshell. So a variety of instruments, it's reasonably large. So are there any other questions in chat about that before I go and show you some stock images that we've taken beforehand?
So
I think what would be great, there's no questions in the chat at this time, but what would be great if Justin could park the telescope and maybe spin the dome so we can see the dome spin too.
Oh, sure.
that's a really nice camera in there. So is that just a light? That's not an infrared camera because the image is really clear. I'm assuming there's a light turned on the dome.
We actually don't have a light on in the dome. We can flip a light on in the dome.
Really
So
It is a night vision camera, and it does have some red lights on it.
camera. Okay.
yeah,
I was impressed with how clear it was.
yeah. So there we just have a light click on. You can see the flash, but it doesn't really change the quality that much. So
That's impressive. That's nice to be able to see that amount of detail. It's handy, audience, to see what's going on with the telescope in case something goes wrong. You never know.
right. Yeah, sometimes you tell the telescope to point in one direction, and sometimes it goes in the complete opposite direction. So
That's true for big telescopes too.
yeah. So Justin, can you spin the dome for us? All right, so if we just enlarge the cameras a little bit, whoops. There we go. So you can see the dome is slowly rotating. Unfortunately, the cameras, I don't think these pick up sound. So this actually does make a really kind of a sci-fi interstellar noise when it's spinning. I wish there was a way to broadcast that because it's a really interesting sound.
Yeah, you can hear it, but just not over WebEx. So it's probably playing on Justin's computer right now, but it won't broadcast over WebEx, unfortunately.
Yeah. No.
Or Zoom, for that matter.
Yeah.
So like a grindy sound with some pew pews. Usually metal moving.
It's a little grindy, but it kind of reminds me of a spaceship about getting ready to go into light speed.
That's also because of the shape of the dome. You're getting all those reflections inside the shape of the, the sphere that is the dome.
Mm-hmm.
Man, I wish I could hear the sound of it getting ready to go to light speed. That sounds pretty cool. I know you're making reference to fiction. But,
yeah, that's what it sounds like to me. But anyways, yes. So Justin spun the dome a little bit.
Yeah, let's have him park the telescope so we can watch it move one more time, and then you can go on. And while he's doing that, we have a question from the audience. Did Peter say you got a picture of Jupiter during the talk? Oh, we're not going to show you that picture because it was just very bad because of the clouds. But William, after we watch the telescope move on the webcam, we're going to show pictures that we have taken with the campus telescope in the past when the weather was more cooperative. We have had actually a little bit of precipitation come through just in the past little bit. Go ahead, William, back to you.
Okay. So as Peter said, we'll just wait for this telescope to finish moving. And then once that's done, we have a few images that we'll show you. So we've taken some images of Jupiter and Saturn beforehand a little while ago when the weather was good. So we can go ahead and show that to you, and a few other images, I think, too, depending on the time and interest. So what I'm going to do is I'm going to actually turn it over to one of our volunteers, Andrew Siddall. If you would like to go ahead and take control, Andrew, and pick whichever one you want to start with, Jupiter or Saturn. We have a couple images there that you can talk about. So if you would like to go ahead and just tell us about Jupiter and Saturn.
Hello, can you guys hear me? All right, perfect. I guess I'll choose this picture right here of, oh, that's a good one. Let's see. This first picture of Jupiter, I guess. So I just opened that up really quickly.
Oh, yeah, that's a glitch. That shouldn't be happening. Go ahead and
okay.
That. Yeah.
It looks like a good picture.
Yeah, let's
one
see.
second. Okay. Would you like, should I click it again? Okay, there it goes.
Oh, there we go.
So there is a picture of Jupiter. That's pretty clear. You can see the bands on it. So a little bit about Jupiter. It's actually the largest planet in our solar system, and it's about 300 times the Earth's mass and about 1,300 times the volume of Earth. And it's also the fastest rotating body in the solar system at about 10 hours, and it has a 12-year orbiter period. And because it has a very fast rotating speed, it has a very famous great red spot, which is basically like a giant storm. And it's about 2 to 3 times, it's about 2 to 3 times the Earth's diameter. So it's really huge, but what's funny is that in recent years, it's actually kind of shrinking in the last century and a half, and we really don't know why, but there's that. It's really interesting. If you notice on here, there's a lot of bands. There's these dark bands and light bands on it. So all these bands are actually different gases sinking and rising in areas called belts and zones. And they're different colors because of the temperature and chemical differences. And what's really cool is that if you've ever seen documentaries or any kind of video of them, if next time if you notice, you'll see that the gases in those bands and zones are going in opposite directions. So that's pretty interesting. But overall, the planet is mainly made out of hydrogen and helium, and it's about 4.2 astronomical units away. So 1 astronomical unit is a distance between the Earth and the Sun, which is about 94 million miles. So it's about 4.2 times that. So if I went a little fast, I'm sorry. You guys have any questions about Jupiter?
We actually do have a question in the chat. Andrew, you're doing a great job. This
Oh,
is
cool.
Andrew's first time in front of an audience doing our telescope tour. So you're doing fantastic, Andrew.
Okay, thank you.
The question from Alex is, could someone ever safely explore Jupiter? And you could take your best attempt at answering that one.
It depends on what you mean by that, I think. If someone was ever to physically go into Jupiter, you'd be okay for a while. I'm not sure for how long. I think I remember reading about it being maybe just a couple hours or so until the pressure just gets really crushing. And at the center of the planet, actually, the gases are so condensed, it's almost like a solid towards where the core is. And because it's just got so much mass and so much heat as well, it would crush really quickly. So you could probably go there only in the top layer of the atmosphere. But as you go deeper, you would not be able to survive. And I don't think there's any instruments either that we currently know of. I mean, we can barely have instruments on Venus without getting crushed really quickly. So in Jupiter, unless it's the way future, I don't think we're going to ever be able to go anytime soon. Yeah.
Yeah, no, that's a good answer. Okay, great.
Any other questions about Jupiter? Anyone? Okay. I guess we can move on to, let's see, Saturn. Okay.
And while he's bringing up Saturn, I'll just say if you come back in 2 weeks, Jupiter and Saturn will still be up in the night sky. So if we have good weather in 2 weeks, we'll be able to take a look at them live and show you these views. Back to you, Andrew.
Yeah, that would be pretty cool. I want to see it live too. So here we see Saturn. Okay, now it's zoomed in. So you can see its distinct rings. So Saturn's actually it's the second largest gas giant after Jupiter, and it's actually significantly farther away from Jupiter. What's interesting is people have this image of all these planets being close together and relatively similar distance away from the sun. But when you get to about the gas giants, each one gets substantially further away than the previous one. So Saturn's around 7 astronomical units away from Earth. So that's 7 times 94 million miles. That's incredibly far away. And it's about 100 times the Earth's mass, which doesn't seem like much if you think about it, considering it's the second largest planet. And it's really light. So it's just like Jupiter. It's also mainly hydrogen and helium. But if you had like a theoretical giant space bathtub, it would actually float in it because it's so light. So it's really not dense at all. Saturn has a lot of moons. It has over 80 moons. But the big ones are, you guys have probably heard of Enceladus and Titan. So Enceladus and Titan are the moons with a pretty substantial atmosphere. And they're said to have possibly have life. Enceladus is an interesting one because actually in October of 2015, Cassini did a flyby, I believe, in the southern region. It was only like a mile or a few miles from the actual moon, which is incredibly close. And it took samples of some plumes that were spraying out from one of the geysers, and it detected organic molecules. And that's actually a really, really big deal because that could mean that there's even if there isn't life, there's the ingredients for life there, and it has a liquid ocean underneath it as well. So that's something that scientists are going to visit in the future with probe missions.
Yeah, that's right. They're actually studying future probes to Europa and Titan. It's really awesome. I think I just saw a news article about a design for a submarine for the oceans of Titan. That was really cool. So we have another question about Jupiter. Do you have any theories about the shrinking of the Great Red Spot? And of I honestly don't know the answer to that one. I don't know if you know anything about it, Andrew.
I actually am not. No, I don't know anything about that. Yeah, I just know that it's been shrinking since about a century ago, but I have no idea.
You should watch, what is it, 2010.
Oh, yeah. Yeah, the sequel to 2001. Yeah, that was in the Great Red Spot. Okay.
This is an interesting one. Is it true
Yes.
about Jupiter flinging asteroids at Earth? It actually helps to fling asteroids away from Earth. So a lot of scientists think that that's probably one of the reasons that life is possible on Earth this long, is because we have it as it kind of defends us from asteroids. It slingshots with its immense gravity asteroids that are lingering in a solar system in our asteroid belts.
Yeah, it's the bouncer of the solar system. It just says, "Hey, get out of here."
It just kind of tetherballs them away, so that's a good thing. Yeah.
Yeah, well, that's
I'm pretty
great, Andrew.
sure. Are there any that could get flinged to Earth though? Maybe not as often as it does away, but
We'd have to be incredibly unlucky in that regard. Yeah.
right. Yeah.
The period early in our solar system when it is thought that soon after the formation of Jupiter and Saturn, that the movement of Jupiter and Saturn sent a large number of bodies into the inner solar system, called the Great Heavy Bombardment. But even that sometimes is debated amongst scientists today. What caused that? Okay, so it's I just want to let us know it's 10 of 10, and I just want to thank all of you for joining us for this long, and we're going to finish up real soon. But William and Andrew, is there else you wanted to share?
Oh, sorry. What was that?
I was asking William and Andrew if there's anything else you wanted to share.
Oh no, that's all I have for now. But if anybody has questions in chats, yeah, I can answer them.
Awesome, thank you, Andrew.
Yep, thank
William?
you.
So it really depends. We do have more images, but we'll be here all night if we go through all of them. We're already about to hit the 2-hour limit. So if there's interest, I can show you all some transit light curves.
Yeah, why don't you show us a transit light curve, and then we'll end the night on time.
I want to see.
Okay. So if we just mosey on over to our transits folder, so let's get one that's really pristine. So what we have here is a bunch of data points, and let's just ignore everything except this top data set right here that's in blue. So what we're looking at is the transit of a planet in front of its host star. So this is a very, very beautiful, very pristine transit here. And usually they aren't this clean cut. There's a lot of noise in the data. I wish we had a noisier, more realistic one to show. But this is what the real data that we do see when we point our telescope at a star and observe its light curve. Of course, it doesn't have to dip like this. It could just remain flat, in which case there's not really a planet there. But if we do see a dip like this, it doesn't necessarily mean that it is a planet. One other possible thing is that it could be a binary star system. And binary star systems, they're neat, but when we're looking for planets, we don't really care about binary star systems. And what's interesting is that from the shape of the transit curve, you can reasonably infer whether or not what you're looking at is a eclipsing binary or an actual planet. And the reason is that planets tend to have a much more flat bottom transit. Like this one, whereas a eclipsing binary would have something that's not as flat. It would just kind of be more ovalish. So that is a piece of data. These other data points here, they are reference stars. And without going into too much detail, the way we actually analyze the data and to get stuff like this is we have, let me pull this up. The target star we actually care about, that's in green, And then in the field of view, we have a bunch of other stars, and these are the reference stars that we compare the brightness to. So what happens is if all of these stars dip in brightness, so the green star and all of the red stars, they all show a dip in brightness, well, that dip is probably just an artifact of, say, the atmosphere. But if something in the green aperture star has a dip in brightness and the reference stars don't, then that's a good indication that whatever dip in brightness we see is actually real and coming from that star. So what we're seeing here with these lines, with these data points below, is just the light curves of the reference star, and you can see that they're pretty flat. Nothing's really changing there. So that's the gist of the light curve. Justin, since this is your research area, I don't know if you want to add in anything else, or Andrew, if you want to add in anything else, or if there are any questions.
You pretty much covered it. So if there's any more questions, go ahead and ask.
It's hard doing Zoom meetings when there's when you don't have the one-on-one in-person interactions and there's all silence. So I'll fill that silence for now. We don't have any questions at this time, but if you do have any final closing questions in the chat, feel free to post them. In 2 weeks, our speaker will be Dr. Curry, NASA Ames, who Dr. Tanner and I know well. And he will be actually talking more about exoplanets with a different technique for finding them. We have some fantastic speakers from Tech, Dr. Luisa Ribol, and others coming up in the rest of the semester. We'll learn about young stars and these from a NASA JPL scientist, Dr. Var Jongorian. And so just if you want to find out more information about these, follow us on Twitter at GMU Observatory or at science.gmu.edu/observatory. We do have one final question, and this will close us out for the night. From Sarah Doan, apologies if I mispronounced your last name. Is the difference of curve shape between the exoplanet and binary the time of the transit? Good.
Do you want to answer that one, Justin?
Let me look at the question again. I didn't quite catch it. Oh, the difference of the curves, the shape of the curvature. It's not have to do with the timing of it, but the way the body is blocking the light. So the flattening of the curve that you see for the planet, if the planet is in front of the star, well, you have that curvature. Let me, there we go. So if you look to the left, you will see that dip in part. We call that an ingress, and that's when the edge of a planet crossing in front of the star. And then when the other side of a planet crossing in front of the star, so the entire planet is in front of the star, and you see the flat bottom part. And then when you get to the right side, is when the edge of a planet starts leaving the star. So and that's the part where we call the egress. So as a planet is passing the edge of a star, it's blocking less of a light. So as it finally move on completely out of the stars, then it go back to the norm, what we call a normal, the flux from the star. The same thing is happening with the eclipse. Eclipse in binary is like what William say, you have a different shape, and it's because the eclipse in binary, which is basically another star, which is somewhat of similar size, could be bigger, could be smaller, so you end up with a different shape due to the way it's blocking the host star. I hope that pretty much a satisfactory answer.
Yeah, that's a great answer, Justin. Largely, it's kind of interesting The math of the shape of the light curve, the brightness of the star, is a function of time. Sarah asked, because the eclipsing binary is also giving off light. That is part of it. What it actually has to do with more primarily is that it's kind of math of overlapping circles. So with a star and a planet, you've got a circle and a little circle. So the little circle passes in front of the big circle, and so you get a big dip in brightness, and then nothing, 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 and then a big jump in brightness. When you have two stars passing in front of each other at roughly the same size, you get them passing in front of each other, and then the dip starts out small, and it gets bigger and bigger and bigger and bigger, and then the dip starts going away slower and slower and slower. And so that's what causes the difference in shape. It has to do with the differences in the size ratios of the diameters of the bodies that are passing in front of each other. There are additional other second order effects, as we call them, more minor effects, that cause the edges of those things to be curved, something we call limb darkening. So thank you all for joining us. We're out of time. We encourage you to come back in 2 weeks. It's been a pleasure, and stay tuned, and hope for clear skies in 2 weeks. And last but not least, thank you to Dr. Tanner for joining us and presenting on her work tonight. Thank you so much. Okay, good night all.